Yesterday in our lesson, we talked about representing relations as sets of ordered pairs. Then we put that into a table. We did mappings, we graphed it, and we found the inverse of a relation. We're going to continue with working with relations again today. So once again, just a little review. A relation is just a set of ordered pairs. So if I have 5, 3, 2, 3, 3, 2, that's a set of ordered pairs, and those are known as a relation. If I wanted to look at the inverse of that relation, remember the inverse is where I just switch from. So the inverse of that ordered pair, 5, 3, we just switched the order of the coordinates, so it becomes 3, 5. So the inverse of this one would be 3, 2. The inverse of this one would be 2, 3. Just a little refresher, the different names for x values is the independent variable, the input, and we talked about this one a lot yesterday, the domain. The y values are known as dependent variables, the output values, or the range. And once again, we know that a set of ordered pairs is just called a relation. Sometimes relations have a specific purpose. Like if I have an equation, y equals 3x plus 2. There's a set of ordered pairs that is a solution for this equation. That means when I plug in any given x value, when I plug in, let's say this 1 we'll plug in 1 for x. If I plug in a 1, then 3 times 1 is 3, plus the 2 more from my equation up here. I'm just taking what was here, plugging in a 1 for x, and solving. 3 times 1 is 3, 3 plus 2 is 5, so I know that my y then is equal to 5. So now I have an ordered pair, 1, 5, that is the solution for this equation, y equals 3x plus 2. If I plugged in a 2, then I would have 3 times 2, which is 6. 6 plus 2 more is 8. So an ordered pair for this equation would be 2, 8. So when I have a group of ordered pairs that is a solution for a given equation, it's still a relation, but this relation now has a specific person. I keep saying person, a purpose. They have a specific purpose. They are the solutions for this equation. They're not a person. Okay, so y equals 4.2x. Let's say I want to graph this. There's a couple different ways we can go about this, and we're going to look at some different methods as the year progresses. But what I want to look at today is just plugging in a group of x values, solving for y, and then plotting those ordered pairs. So I'm going to start by giving you 0.1. 0.1 is my value for x, so I want to plug it in place of the x, and I'm going to solve. 4.2 times 0.1 is 0.42. If I plug in 0.25, 4.2 times 0.25 gives me 1.05. I'm just multiplying. Do that for a set that's given, and now I have a group of ordered pairs, 0.1, 0.42, 0.25, 1.05, 0.5, 2.1. I can plot each one of these ordered pairs. Those are ugly. I don't want to plot those. Those are decimals. Let's look at one that's a little more simple. Say I have y equals 3x, and I tell you the domain is -2, -1, 0, 1, and 3. I want you to find a set of ordered pairs that is true for this equation that we can graph. So given the domain, remember the domain is just a set of x values. So all of these numbers up here are my x's. I'm going to plug them in place of x. So I'm going to start off 3 times -2. 3 times -2 is -6. So I've got an ordered pair, -2, -6. If I plug in the -1, 3 times -1 would be a -3. So I have the ordered pair, -1, -3. If I plug in a 0, 3 times 0 is 0. So I have the ordered pair goes through the origin, 0, 0. 3 times 1 is 3. 3 times 3 is 9. So now I have this listing of ordered pairs that I can now graph. So if I want to graph this one, -2, -6, I'm going to go over 2 on my x-axis and down 6. 1, 2, 3, 4, 5, 6. I'm going to put my point. -1, -3. Go to the left 1, down 3. Going through the origin, 0, 0. Okay, then I have a +1 and a +3, so I go to the right of 0 and up 3. And a +3, +9. So to the right 3 and up 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I skipped 2, which it wasn't part of my domain, but I know that it would be in here. We can tell by looking, which being a math teacher, I already knew this was a linear equation because we have a slope and then the x and then our y-intercept will be +0. We'll get to that later on this year. But anyway, we can graph this, and of course the graph is a straight line. If I had plugged in 2, 3 times 2 is 6, so I would go over 2 and up 6. That wasn't in my domain, but that's part of it. So, as you can see, the graph is a straight line. Let's try another one. This says in 2002, 12 countries switched to using the euro, which is just a form of currency. Suppose the exchange rate between US dollars and euros is $1 equals 1.11 euros. The equation E equals 1.11D can be used to convert dollars to euros. Find how much U.S. money, or U.S. dollars, a traveler spent given the following table. So, for his hotel, he spent 90 euros. We need to find out how much money that cost. So, we're going to use the formula. E equals 1, oops, that's not an equal sign. E equals 1.11 times D. Well, we don't know D, but we know the euros was 90. So, in place of my E for euros, I'm going to replace 90. So 90 equals 1.11 times D. How would I get D by itself? Well, hopefully you all remember from what we've been working on so far this year. In order to get D by itself, I'm going to divide by 1.11. So 90 divided by 1.11 is, I believe, 81. Let me get my calculator. I don't want to screw that up. 90... Let's see here. 90 divided by 1.11 is approximately 81. It's 81.08. We'll stick with the 81. Okay, 50. 50 euros equals 1.11 times the number of dollars. We don't know the number of dollars, so I'm just going to divide 50 divided by 1.11, and I get roughly $45. Same thing for the 30. 30 divided by 1.11. $27. And then the 20 euros divided by the 1.11 for the exchange rate gives me $18. So how much money did our... So we're looking for how much money he spent altogether. So I would just add these values. 81 plus 45 plus 27 plus 18 gives me a total of 171 US dollars. Now, if I wanted to... Okay, so there we have it. -1. Remember our song, a negative times a negative. Multiply or divide, it's an easy thought. Same signs are positive. Different signs are not. Here we've got different signs, not positive, it's negative. Okay, so... -4 times -1 is a +4. -4 times 0 is 0. -4 times 1 is -4. -4 times 2 is -8. So then I have my listing of ordered pairs. -1, 4. I plotted it. -1, 4. 0, 0. 1, -4. And 2, -8. So there is my graph. Now I need to write out my range. What is my range? It's just my y values. We always put them in order from least to greatest. So it's -8, -4, 0, and 4 is the range for this given equation. Okay, this one is not so friendly. 4x plus 2y equals 8. I'm given that the domain is -2, -1, 0, 1, and 2, and I'm asked to solve for the range. That means I'm wanting to solve for y. So if I was given this problem, you could plug in x and then solve for y, but it'd be a whole lot easier if we manipulated this equation so that y is by itself. So that's what I want to do. I want to get rid of this 4x. I want to move it to the other side of my equal sign. So if I have a positive 4x, in order to get rid of it, I'm going to subtract 4x. Whatever I do on one side of the equation, we know I have to do to the other. 8 and 4x are not like terms, so I can't do anything with that. But I have 2y equals 8 minus 4x. Remember, I said I wanted y all by itself. That means I've got to get rid of this 2 that's being multiplied by y. The inverse operation would be to divide by 2. Whatever I do on one side, I have to do on the other. 2 divided by 2 is 1. 1 times y is y. So I've accomplished my goal. Y is now by itself. 8 divided by 2 is 4. 4 divided by 2 is 2. So now I have it where I can plug in my values of x and solve for y. And I've already done that for you over here. If I plug in a -2, I end up with 4 minus a -4, which becomes 4 plus 4, which is 8. If I plug in a -1, I have 4 minus -2, which becomes 4 plus 2, which is 6. If I plug in 0, 4 minus 0 is 4. And then plug in 1, 4 minus 2 times 1 is 4 minus 2, which is 2. Plug in 2, 2 times 2 is 4, 4 minus 4 is 0. So I end up with a set of ordered pairs, -2, 8, -1, 6, 0, 4, and I could keep on going down the list. And this set of ordered pairs is called a relation. Anytime I have a set of ordered pairs, back to our vocabulary, it is called a relation. Okay, that is all. I'm sorry this video had so many pauses and interruptions. What I want you to do is practice this in your book. If you turn to page 214, I want you to do numbers, let's see here, 6 through 9, and numbers 32 through 38. 38 is your challenge question, and you can do it. First, convert it to where you have y all by itself, then plug in the x's. If you have any questions, don't hesitate to ask.